since I walked away. I never thought that I could feel as great as I do today. 'Cause you were nothing but a big mistake, and life is wonderful now that I'm rid of you.
Oh, I must have been crazy to have stayed with you. I can't believe I thought I was in love with you, but now the scales have fallen, I can really see. And I say, go to hell, 'cause that's where you took me.
Well, I felt better since I slammed that door. You always cramped my style, I never noticed before. It's been a non-stop party since I flew the coop. I can't believe I fell for such a loser like you.
And is it any wonder that I felt so blue when I was always having to put up with you?
Oh, here we go again, just lay the blame on me. Don't say another word, 'cause sweetheart, you're history.
I bet you're loving every minute of it. Sitting in the kitchen, eating meager meals with the curtains closed. God, be a bedsit martyr, babe. I don't give a damn anyway. 'Cause I met this girl, and she's so good to me. She's really beautiful, fantastic company. Oh, when I'm with her, I realize what love can be, because she's 50 times the person you will ever be. Oh,
Good luck, mister, do you think I care? Since you've been gone, the offers have been everywhere. I've got a million guys just lining up for me. I've turned a corner, boy, my life is ecstasy. Well, I've been in heaven since I walked away. I never thought that I could feel as great as I do today. 'Cause you were nothing but a waste of space, and life is wonderful now that I'm over you.
Welcome back. It's Thursday. This is Computer Science 3, CSCE 310. And today and for tomorrow, we're going to continue looking at several various data structures. Yesterday, we started talking about, we gave a quick review on binary search trees. And of course, their shortcoming in that they might have there might be a degenerative tree where you've got a depth of linear depth of order n, meaning that it's no better than a linked list. So what we're going to do today is we're going to introduce the first notion of a balanced binary search tree. And the first, there are dozens of these things. There are splay trees, 2-3 trees, B trees, AVL trees, A trees, A star trees, etc., etc. There are literally a dozen different balanced binary search trees. Each one is used in different applications. We're not going to go over all of them, of course. Instead, we're going to look at AVL trees and 2-3 trees, which are a special case of B trees today. So to do that, we're going to have to get some definitions out of the way here first. But before we do that, I want to remind you that we do have live Piazza Q&A. So if you've got questions or you want to bring something to my attention, like the quality is not as good as it should be of the stream, please let me know about that. Okay. So before in order to define AVL trees, and again, the AVL simply stands for the people that came up with them, that developed them. It's the first letter of each of their names. So we're going to have a couple more definitions here before we do this. The height of a tree, of a node, U, in a tree, denoted as h sub u, right, is the longest path to any of its descendant, if I spelled that correctly, leaves. Right, there we go. I think that that's spelled correctly. Descendant, right? This is a little bit different from the depth because the depth is with respect to the root, right? From the root down to any node, that's the node's depth. Or if you want, since it's undirected, you can view it as a relationship from the node back up to the root. That's the depth. But the height is with respect to its leaves, right? So the other way down, right? The height of a leaf, so we need some corner cases here. The height of a leaf is 0, right? Because it has no descendants, therefore the longest path to any of its descendant leaves is 0. There are no leaves, right? But we also need another corner case here. The height of an empty tree is -1, right? So if the height of a leaf just by itself, you can, again, it's a single node, so you can consider that to be a seed if you want. And it has depth 0, it has height 0, and by convention, if we take that away, then it's even less. So what's less than 0? -1. Okay, it's just a convention that's going to help us with the mathematics. Right? The height of a tree is the height of its root. Right? This is the same definition as as the depth of a tree. Right? Both of those end up being the same because it's all with. If you focus only on the root, then now everything is with respect to the root. Okay. All right, let's go ahead and take a look at a really quick example here. Let me go ahead and draw a tree, and I'll just draw a generic tree here with nothing in its roots, or nothing in its nodes, excuse me. All right. There we go. So if I look at, again, if I look at a leaf node here, by convention, its height is going to be 0, okay? If I look at another node here with, and I look at all of its descendant nodes, the length of the longest path to any one of its leaves is going to be 1, right? In fact, it's the same on both of these. The height of this node is, of course, there's no left child here, so the length of the longest path down to the left is 0, but we do have a right child, so the length of the longest path to any one of its nodes is going to be 2. To any one of its leaves down here. Likewise, what about this one? Well, you can, kind of just figure out a pattern here, 3 and 4. Well, what's the depth of this tree? 1, 2, 3, 4. It's the same up here. So those are the heights. The height here is going to be 0, 0 of all of these. The height here is 1, 3, etc. All right? Good. So you can also, inductively view this that if I want to know what my height is, I don't need to look at all of the leaves here as long as I'm maintaining the height in all of the nodes. Well, I know that the height of my right child is 2. I know the height of my left child is 1. Therefore, this is larger. So my height is at least 2, but then I have to get to that node. Therefore, my height must be +1 of the maximum of these two things. So I end up with 3. So that's the concept of the height of a tree. It's with respect to the leaves, okay? That allows us to define a balance factor. The balance factor of a node, U, denoted, and we'll just use BF of U, right, is the height of its left child / tree minus the height of its right child / tree. Right? So what does that mean? Well, again, let's go over here to our example here. These are all heights. Let me go ahead and use a different color here for balance factors, BFs. Right? So what's the balance factor? Well, let's just go with something simple here. What's the balance factor? What's the height of the left tree minus the height of the right tree? 0 minus 0. So this is going to end up being 0. Right? What's the height of of this node right here? It's going to be 1 minus 2. So it's going to have a negative 1 there. It's a negative 1 balance factor. What about this? 3 minus 0. Its balance factor up here at the top is going to be negative 3. Okay? Oh, sorry. 3 minus 0. It's positive 3. Thank you. There we go. All right. All right. So some corner cases here first. So that's the balance factor. A balance factor of 0 indicates a perfect balance. Right? So let's go back over here to the one that I wrote right here, 0. It's perfectly balanced because it has its left subtree has the same height as its right subtree, right? In fact, what's the balance factor of this guy right here? Remember that the height of an empty tree is negative 1. The height of its right child, which is also empty, is negative 1. Negative 1 minus negative 1 ends up being 0. Right? Negative 1 minus negative 1. So they end up canceling each other out. So a balance factor of 0 indicates a perfect balance. A positive balance factor indicates a skew to the left. And a negative balance factor indicates a skew to the right. Again, let's look at our example. Remember that I corrected myself and said that this is 3, this is positive 3, and that's because it skews to the left. The left subtree here is much deeper than this simple seed over here, this right subtree. Whereas this is negative, that means that this tree has higher height, a greater height than this one over here. And it has nothing to do necessarily with the number of nodes in that tree, like the weight of the tree, if you want to consider that. It only has to do with the height of the tree, right? So we don't want, our goal here with AVL trees is that we don't want unbalanced trees, right? In general, an AVL tree, AVL tree is one in which is a binary search tree, of course. Is a binary search tree such that all nodes have a balance factor of 0, 1, or negative 1. Right? So we're going to allow them to be a little bit unbalanced to the left or to the right, depending on the positive or negative there, or perfectly balanced, 0, as all things should be, but not too unbalanced. So if we have a balance factor of 2 or negative 2 or 3 or negative 3, we're going to want to rebalance it, just like this one. This is way too far unbalanced to the left. We never should have gotten to this situation to begin with. 3 is way unbalanced. So anytime that we have an unbalanced node with a balance factor of 2 or negative 2, that means that we're going to invoke those rotations that we covered yesterday. In fact, let's review those. On very simple, small trees, 3-node trees here. All right. So the first one we looked at was, say, 30, 20, and 10. Okay. So what are the balance factors here? Well, the balance factor here is negative 1 minus negative 1. It's perfectly balanced, right? The balance factor here is, what's the height of this tree? The height of this tree is going to be 0 minus the height of this tree. But remember, an empty tree has height negative 1. So it's actually going to be 0 or minus negative 1. So it'll end up being positive 1. Right? And remember, positive means that it skews to the left. And that's exactly what's happening for this node. There's one left child, but there's no right child. So it skews to the left, plus 1. What about this one up here? Well, the height of this tree is going to be 1. The height of this empty tree over here is negative 1. So 1 minus negative 1 equals plus 2. right? So we have an unbalanced factor here of positive 2. Again, positive indicates that it's skewed to the left, and that's exactly what's happening in this case. So what we need to do is we need to invoke a right rotation. And remember, when that happens, that 20 comes up to be the new root, 30 becomes the new right child, and 10 is the left child. Right? Now, again, let's go through the balance factors here. You can go ahead and just say that any leaf has a balance factor of 0. That's pretty easy. And you can see that this is now perfectly balanced. A balance factor of 0 minus 0, so it's going to be 0 up here. Right? That doesn't have. It's not this 0 minus 0. This 0. Remember, the blue is indicating a balance factor, not the height of the tree. Okay. And if as far as practical implementations go here, as an aside, if you were to actually program this, then you would be keeping track of all this metadata and updating it. That here's a node. Not only does it hold a key and maybe a value, it also holds and its left child and right child and parent, but it also holds metadata like the depth. Right? It holds its depth. It holds its height. And maybe even its balance factor. Okay. The other way around, where we do a left rotation, let's go ahead and look at that really quickly. Oops, sorry, 10 at the top, then 20, then 30. And again, it's just a mirror image of this. This is going to have a balance factor of 0. This will have a balance factor of -1. -1 minus the height of this thing right here is 0. It doesn't have anything to do with that that balance factor right there. So -1 minus 0 gives you -1. -1 minus 1 gives you -2, right? It is skewed to the right because we've got negative values here. And when we look at its right child, when we look at the left child over here, we also see that it's still skewed to the right. So that tells us that we need to do a left rotation, and we end up with the exact same configuration over here. Okay. What about those two other rotations that we looked at? What if we have 30, but then 10 and 20? Okay. So a little bit different configuration here, but again, we can go ahead and compute the balance factor. The balance factor there is 0. The balance factor here is going to be -1 minus 0, so it's -1. The balance factor here is going to be 1. That tree has a height of 1. That tree has a height of 0. Of -1 on the right subtree right here. So 1 minus -1 ends up being 2. Sorry. They cancel out, and so I have 2 here. It's unbalanced to the left. Positive indicates unbalance to the left. But then look at its left child. Negative indicates unbalance to the right. So we need to correct for this. To correct for the unbalance at the right, we do a left rotation. To correct for the unbalance at to the left, we do a right rotation. And this gives us an LR rotation. Right? We move 20 over there. Right? This is just an intermediate step here. This is not the end result. We end up with something like this. After we rotate 20 up, now we rotate over, and our last configuration here is what we're used to, the perfectly balanced binary search tree with 3 nodes. All right. Likewise, what does it look like when we've got a mirror image of that? So the mirror image here is going to be 10, then 30, then 20. So just looking at this, without even computing any balance factors or anything like that, we know that it's skewed to the right, and its right child is skewed to the left. So I will need to be doing a right left rotation. Right? And again, let's look at the balance factors of this thing. This is 0. This is going to have a balance factor of 0 minus -1. So it's going to be 1. Positive, indicating a skew to the left. This is going to have a balance factor of -1 minus 1, giving you a balance factor of -2. Negative, indicating a skew to the right. All right, so skew to the right, you look at the child, right? If it's still positive, if it's positive, then you know that it's skewed to the left and you need to do a right-left rotation. If it were like the examples that we looked at before, where this is negative and this is negative, that means it's skewed all the way to the right. If it's positive and positive, then this gives you a way to distinguish which kind of rotation you actually need to invoke. Because we're only ever inserting one node at a time, the balance factor, as long as they're all 0, 1, or -1, will only ever be able to be disrupted by at most 1. And we only need to do a rotation there. Once we rebalance it, then that automatically sets that -1 or +1 back to -1 or that -2 or +2 back to -2 or -1 or +1. So we only have to make local adjustments in the binary search tree in order to fix everything. Okay, so let's look at an example here, and to do that, instead of drawing, I'm going to go ahead and use a visualization tool. These are a dime a dozen online. You can find, you can use any one that you want to verify, or even take snapshots if you want to. For your homework or just to understand them a little bit better. This is an AVL tree visualization. Let's go ahead and insert. Let's see. We'll go ahead and insert, like in the lecture notes, we've got 8, 4, and 7. So let's go ahead and do that. 8. Oops, come on. 4. It's giving me random numbers. I don't want those. 8, 4 gets inserted as the new left child of 8. And at this point, let me go ahead and zoom in for you. There we go. That's a little bit better. Let's go ahead and insert 7. Now, before I do that, where is it going to get inserted? Let's predict here. 7 is less than 8. It's greater than 4. And so it'll be the new right child of 4 over here, right? But that means that we are skewed first of all to the left, then to the right, and so we need to do a right-left rotation. And what's going to end up happening is that 4 is going to become our new root, or 7 is going to become our new root. And I don't like that visualization because it gives the misimpression. It just swaps things around. That's exactly what's happening, but it doesn't do that nice little rotation. Okay, I should have found a better one. But anyway. Let's go ahead and insert now, say, 3. Right. Now, is this going to cause a disruption anywhere? Well, we can say right now it's got to be inserted somewhere at the next level. And there's no, if we try to mess with the tree at all, try to move something up, then necessarily something is going to be pushed down, because pigeonhole principle, basically. You can only fit 3 nodes in the first 2 levels, so this is probably not going to end up with any sort of unbalance. Okay, it's going to be the left child of 4. Right? Everything's fine. Let's go ahead and think about this for a second, though, and maybe over here on our scratch paper, you can actually see it on the same screen. What is the balance if 3, 4, 7, and 8? Let's see why there was not any rebalancing here by computing the balance factor of all these things. 0, of course, and 0 over here. The balance factor of this is going to be 0, because the height of a leaf is 0, minus -1, so it's going to be +1. What about the balance factor here? 1 minus 0 is going to be 1. Right? So 1, 0, +1, that's completely allowable in an AVL tree, right? There's nothing that's unbalanced yet. But the second that we insert something else, well, we could insert something that hangs off of 4 here, that other children of 8, and we would not disrupt the tree at all. But let's go ahead and insert, say, 2. right, as in the notes. Before we do this, before I hit the button here, let's predict what's going to happen. 2 is going to come down to 7. It's less than 7, so less than 4, less than 3, and then we've got something over here. Right? So let me go ahead and get rid of all these old balance factors. Right? What's the new balance factor here? If we know that this is going to end up inserting 2 right there. So it's going to be 0, of course. 0 minus -1, so this will be 1. It is unbalanced to the left, only slightly though. Perfectly fine still here. Now at this node, we know that it's going to be 1 minus -1, so this will be 2. In other words, positive, skewed to the left, positive, skewed to the left, and so we're going to have to do a rotation here, right? But we're doing it on this part of the tree only, right? We're not going to be affecting anything up above that tree because we're only making local changes here. If we ended up having to make global changes, in other words, we have to change everything in the tree, then we potentially have an inefficient algorithm because we'd have to traverse to all the cousins and stuff like that, right? But if we only have, and we'll talk about this when we look at deletions, if we do have to make additional changes, then that might propagate up the tree. But for inserts, you don't have to do that. All right. What was the balance factor here before? It was 1. Right. It does temporarily become unbalanced at this node, yes, but the rebalance here will end up meaning that we reduce the entire height of the subtree, and so the entire height of the subtree will be unchanged after the insert and rotation. So let's go ahead and do that. I'll hit the trigger now, and we'll see what it looks like. There, and of course 3 and 4. They need to rotate over, right? And everything is balanced. Again, what is the height or what is the balance factor of this 7 right here? Well, it's 1 minus 0. It's still positive 1. Just like before, it is unchanged. As long as you're always fixing it when you hit 2 or -2, then this will work out and you don't need to propagate that up. Because whatever the height was before, you've increased it by 1 because you're only ever inserting 1 element at a time. But then you'll correct it with a rotation left, right, or right, left, and that ends up with the same height that you had before, meaning that you're not going to disrupt anything up higher in the tree. Let's keep going here. What else do we want? Let's go ahead and go with, let's see, what's my list of numbers? We inserted 2. Let's insert 5 now. But let's predict what's going to happen here. So 2 is going to come down, less than 7, greater than 3, greater than 4, and so it'll become the right child of 4. Right? Now let's just predict what, let's write the configuration of what that's going to look like off to the side here. Oops. So 7, 8, 3, 2, 4, and 5 is going to end up being right here. Okay. What are the balance factors? The balance factor here is going to be 0. -1 minus 0, so -1. So still okay here. 0 here. Right. 0 minus 1, so -1. Again, it's skewed to the right, yeah. But what about up here now? Up here we have screwed up the balance factor. You do potentially need to recompute the balance factor up for a little bit further than than where you inserted, but you only have to do that proportional to the depth, which is because of these properties that we're developing here is going to be order log n, and so that's fine. You're okay with paying for that because that's what an insert you had to get there to begin with, right? You had to go down the tree, order d, order log n. To get there, so you might as well just work your way back up too. Right? Okay, so what's the balance factor right here? Well, the height of this tree is now 2 minus 0, so we've got 2. We've got a skew to the left because of the positive 2, but if we look at the left child, it's a skew to the right. So what do I need to do? I need to do a left rotation and then a right rotation, right? What is that going to look like? Let's visualize that before the visualizer does this for us. I said I was going to use this visualizer, and then I ended up not doing it because it's a nice tool, but the explanations may need a little bit more here. So what does it look like after I've done this left rotation? Well, 4 has come up, 5 is over there, 3 is over there, and 2 is over there, and it's still hanging off this 7 up here, 8. Right? So I bring that up. It's still unbalanced, by the way, because I didn't change the height of this. I just took I just moved this over here, so the skew is now to the left here. But with respect to this number up here, the root, it's still skewed all the way to the left, right? There's still a 2 minus 0. It's going to still have a balance factor here of 2. So now I need to rotate right here. What is that going to look like? 4 is going to come up to be my new root, right? 8, and so 7 is going to be my, if I just move this over here, 7 and 8 are still hanging off of that. 4, what was hanging off the left there? 3 and 2, right? But what happens to this 5 right here, right? It was the right child of 4. Where can it go? Can it go over here as the left child of 3? No, because everything in the left subtree has to be less than 4. So where can it go? Well, it needs to stay to the right of 4, and so it ends up right here. It swings over, basically. The subtree swings over. We'll look at a fuller example here in a second, but let's go ahead and hit the trigger and see if my explanation was right or if I screwed it up somehow. I want to see what it visualizes it as, though. So swing over, all right? It swings over, right? So that's what it looks like in the end. Verify that, it's still a binary search tree. Great. What happens now? Now I'll forgo the list down here and just go for it. 1, well, that's going to unbalance everything over here, and easily that's just going to be a right rotation about 2. There we go. At this point, we have a full binary search tree. Everything here is balanced, perfectly balanced, because everything has a balance factor of 0. So if anything else more that I insert, as I could insert 2 children off of 1, 2 children off of 3, 2 children off of 5, and 8, and there would be no further modifications of the tree. I think I'm going to let's insert just to show what it might look like. Insert 10. That's going to become the new right child of 8, all the way to the right. Again, it's full up here, so if inserting down here, any rotation would necessarily push something else down. So you know that there's not going to be any rotations there. Let's go ahead and insert 6. There we go. That'll be right, left, right. Right, and so I could fill up this entire third level here by choosing appropriate values, or if I put in, say, 12, let's do one that will actually cause a rotation. What kind of so hopefully if this were a class, I'd ask Socratically, does anybody know what kind of rotation will happen off of this? Oops. Okay, we've got a question. I'll come back to this in a second here. 12 is going to hang off of 10, and then that'll be a left rotation. So that 10 will come up, 8 will be the new left child, and 12 will be still the right child of 10. All right, let's see this in action. And there we go. All right, so the question online is, in the left side example, you said that 1 minus 1 is equal to 0. So I thought that it was, in the right example, you said -1 minus -1. So I'm a bit, I might have screwed up somewhere. And unfortunately, there's no way, we're on a 10-second delay here or so I don't know which one we were talking about. But let me go ahead and just pull in the notes here. So here are the simple rotations. Hopefully this is what your question was asking about. That the balance factors here are going to be -1 because it's empty. The balance factor over here is the height of this subtree here with just B and C is going to be 1. So it's -1 minus 1. So it'll end up being -2. Right? And the other one is, let's see. I guess you're asking about this. The balance factor here is 1 because it's 0 minus -1. It's an empty tree right here. So it ends up being +1. This is going to be the left subtree here has a height of 1. The right subtree here has a height of -1. So 1 minus -1 ends up being +2. Right? Hopefully that was clear. If not, go ahead and post on Piazza, and I'll try to clarify that even more. You can go ahead and play with these tools all you want and come up with visualizations and see how it actually works. Let's take a look at a visualization here of a removal. I don't know if I can make this all that interesting. Let's remove, I don't know. If we remove a leaf, forcing it to become unbound. Nope, that's not going to work. So let's remove 1. That's not going to do anything. All right, let's remove 1. It's just going to remove it because it's a leaf. Changes because, yeah, it's still balanced. Even though it appears to be skewed to the right, that's just remember that the balance is with respect to height, not like mass. All right, so you can have a very, very I don't know what you would call it in an actual tree, but one branch has a lot of lush leaves and is very green, and another branch is very sparse because I don't know, insects have gotten to it. But it's still balanced in that there are 2 branches, right? They're still the same height, even though one is clearly in poor health and the other is better. So let's go ahead and delete 3 here. Remove 3. What's going to happen? All right, just conceptually here, and then we'll let it do our work for us. Well, that will mean that the height of this node right here, the balance factor actually will be restored to 0 but the height of this subtree will then become 0. And so visualize that without the 3 right there. Let me go ahead and pull paper over here, and let's understand what's going to happen with deleting it. Right. So we've got 2 over here, and what else was over there? 4, 7, 5, 6, 10, and I'll come back to it here in a second. I'm just writing it all down. Right. So we've deleted 3. Right. 3 is now gone. What are the balance factors? Let's get some more practice here. The balance factor of any leaf is going to be 0, 0. Right. This is going to be -1 minus 0, so -1. This is going to be, well, this one is going to be balanced. This one is also going to be balanced. 1 minus 1, so it's going to be 0. What about 4, though? This is going to be 0, right? A single node is going to have height 0. What is the height of this tree? It's 2. So -2 is going to be -2. It's skewed to the right. So now we look, left, we look right. They're both balanced, basically. We need to use the balance factor that it was to understand that, okay, well, we need to rearrange this somehow. And basically, we're going to do, I believe, a right rotation here, where we're going to try to make 7 the new root node here. 4 and 2 are going to hang off of it. 7 had 10 before, but what about this tree right here? Right? Where can it go? Well, it's going to, again, swing over here to be, 5, 6. Right? That's where the tree is going to end up. Right? And then, of course, we've got 8 and 12 over here, and that's going to be much more balanced now. Let's go ahead and see it in action. 3 gets deleted. 7 is going to have to come up to be our new root, and 5 swings over, and now everything is rebalanced. Okay. Great. Right. Now, that wasn't all that interesting because it was only one rotation. You can have, when you delete things, you can have a worst case scenario, and I did not bother building it, so I'll just bring over the notes here. Here's the worst case scenario with respect to deleting it, right? Or one of the worst case scenarios where you delete this, fine, you rebalance it, but then that rebalance means that you have to rebalance its parent, right? Because everything over here is still over here. So, okay, go ahead and rebalance the parent by doing a left rotation there. All right, then that brings 30 up, but then now its parent is rebalanced. And here I've just got two generic keys or trees hanging off of 60 here. And so we have to potentially rebalance the parent. Is the worst case scenario because the rebalance might cause disruption to the parent. The parent's rebalance might cause disruption to the grandparent, etc., all the way up. You could end up with having to rebalance it all the way back up to the root. But guess what? Each rebalance is only switching a bunch of pointers or references, and the depth of the tree is only logarithmic. So it's okay that that's the worst case scenario going all the way back up because you're only doing a order D amount of work, and we've got a guarantee eventually that this is going to be the D is order log n. All right. So that's deletion, insertion. Of course, I didn't even mention searching, of course, because it's exactly the same as any binary search tree. You start at the root, go left and right until you found what you're looking for, or you find that it doesn't exist. Okay. All right. Let me know if I answer that question or not, or I need another explanation. Otherwise, let me pull up the general rotations. Remember I said that this thing swings over, or that this entire subtree that's hanging off of it swings over? That's where we come up with these generalized rotations here. That this is an LR let me start with the simplest one. Sorry. Here's a generalized left rotation. So again, -1, -1 meaning it's skewed to the right. I'm skewed to the right, and my child is skewed to the right. So we need to do a left rotation. What happens to the trees hanging off of my child, 2 and 3? This tree swings over to become the new right child of R, right? We inserted A over here, and then A gets pulled up because this tree gets pulled up, because C gets pulled up. Remember Jack and Jill on the hill, right? They're all connected, so pulling it to one side of the hill pulls everything on the other side of the train. Except that to preserve the binary search tree property, we have to potentially swing this tree over to become the new right child. And that makes sense too, because everything in this right tree is greater than R, right? And so C is greater than R. Everything everything in T3 is greater than R. Everything in T2 is greater than R. So this area over here is preserved. But remember, T3, everything in it is greater than R, so it has to be to the right of R. But it's also less than C, so it has to be somewhere in the left subtree of C. So where does it go? The only place it can go is right here off the right child of R, if it exists. Now, when we were looking at the very simple examples, or when we started creating trees, then these trees were swinging over. It's just that they weren't. They didn't have any nodes in them, so it was an empty tree swinging over, and potentially we can check for null values or something if we were to actually implement this, or we could just say that, well, my left child is now equal to that thing over there happened to be null, so my left child is null, right? It depends on how you implement your trees. The generalized right rotation is also similar. Again, this T2 over here swings over to become the new left child of R. R being my placeholder for root, C might be my placeholder for the child. Okay. What about a generalized left-right rotation? So here I've got the root, I've got the child of the root, and then I've got the grandchild of the root. That's why I've used G here. Now this is a little bit more complicated because you potentially have 4 trees hanging off of this thing. So when you do a right rotation, then a left rotation, then a right rotation. Where do all these trees end up? Well, T2 is greater than C, less than G. G becomes the new root, and so T2 has to be in the left subtree, and it also has to be to the right of C because of those properties. Likewise, whereas T3, T1 and T4, by the way, are unaffected. They're still the left child of C and the right child of R. Where does T3 go? It swings over to become the new left child of R. Right? And that's where everything gets rebalanced. And the mirror image of that is going to be a right-left rotation. End result is the same. Okay? All right. All right, good. So we're not going to go through a full analysis here, but understand that because of the balance factors, you can show that the depth of an AVL tree is always d order log n. There we go. Yep. And thus insertion, deletion, and retrieval are all order log n. I don't want to type that again. Right. Observe that the operations of rotation that the rotations are all order 1 operations. You are simply swapping around references or pointers if you've got a programming language that uses pointers instead. That I'm just saying that this child is now equal to that child instead. Now in your homework assignment, you have to come up with some pseudocode to do that, which is pretty easy to do. The only thing that you have to be aware of is that you can't lose references. If I need this tree to swing over, I need to put that into a temporary value so that I don't lose it, right? That in particular node, I need to put that into a temporary value so that, okay, now I can update this child. If I just updated the child and I lost that and I pruned out that entire subtree, that would not be good, right? Deletions, or I should say that insertions are always, or will only make local changes, right? Involving the immediate parent and or grandparent. Updating balance heights and balance factors is order D, which again is order log n, because yeah, you do need to update the parent's height and you do need to update its grandparent's height all the way up potentially into the tree. Deletions may cause ripple rotations up the tree, but each one is only order 1, and so all of them would be order log n. There we go. And it's not that difficult to program these things, but I've kind of shied away from assigning those kind of assignments just because, well, one, there's so many implementations out there, there's so many visualizations out there that it's way too much of a temptation to just grab one of those things. Also, it's pretty they're pretty standard. It's just needless complications. So that's why I ask you to do pseudocode instead. Just come up with a pseudocode for what are the conditions that, which kind of, do I need to do a rotation? And if I need to do a rotation, which type of rotation is it? All right, well, this rotation, how do I switch these things around, right? What child needs to be updated? What parent node needs to be updated? What references need to be updated? And that's all going to be constant time. Okay? All right. So let's look at another type of tree. B trees. Don't ask me why they're called B trees. There are A trees, so maybe they just said, all right, well, the next, just like, why is C called C? Well, because it was the next one after B. There was a language BPCL that Kernighan and Ritchie, I think, had worked on, or one of them had worked on or worked with, and so they just made, all right, well, what's the next? C. Just like C++. Why is it plus plus? Well, that's the iteration operator. It adds 1 to the variable, and so what's the next version of C? Plus plus, right? Not that clever. Why is it C sharp? Some people are using C sharp for this course. Well, because it's music, right? What's the note right above C? C sharp, right? I think C flat would be below it, but I'm not a music person, so I don't know. Right? Go ahead and confirm or deny that on Piazza if you want. All right. So, sorry, want to get to my notes here. Okay, there we go. All right, so what are B trees? B trees are actually used in a lot of database implementations because of their efficiency and because of their flexibility. You can actually tune them. You can make. We'll see this a special case here in a second, but of 2-3 trees, where you can say that each node doesn't contain just one key; it can contain k keys. Right? Every node may contain or may have at most m children. Right? And if it has m children, that means that it needs to distinguish between all those children. So if you've got 4 things here, you need 3 keys to tell you that, oh, it's over here, or it's over here, it's over here, or it's over here. So every node except the root has at least ceiling, L seal, I should have just typed this out before, L seal of m divided by 2 R seal. There we go. At least that many children. Right. So there is a minimum number of children, and there's a maximum number of children, and it's not just 0 or 2, like in a regular binary search tree. The root has at least 2 children, unless it is a leaf. Right? So unless you're just starting out building the tree. Non-leaf nodes with k children have k minus 1 keys. Right? Because again, if you've got k elements here, 4, well, how many dividers do you need to distinguish that? You need at least 3 there, 1, 2, 3, to say that it's this one, or this one. Right? Just like if you've got 4 points or 4 vertices, how many edges do you have to put in to connect them all together in a line? 1 less. Right? All leaves appear at the same level and are non-empty. They all contain keys. It's commonly used in databases because you can take this M factor and you can tune it to be larger or smaller depending on your cache size, so that you want to minimize cache misses, maximize cache hits, or something like that. Whatever your page size is in memory, etc. So you can actually tune these things. But visually, what we're going to do is we're going to focus on M being 3. Right? In other words, we're going to look at 2-3 trees. Right? Every node may have 1 or 2 keys, thus 2 or 3 children. To get that, all you have to do is go back to the definitions I just gave you, plug in M for being 3, right? Has at most 3 children and has at least 2 children. So you don't have a situation where you have just 1 child, right? Only a left and no right. You will always have at least 2 children or 3 children. And that's the simplest case of a B tree. In fact, you can set M to be 2, and guess what you have then? Has at most 2 children, has at least 1 child, and so it's not exactly a traditional binary search tree because of course you can have no children, but it looks more like a binary tree. Right? So let's look at those types of nodes. Oops, there we go. A 2 node is a node containing 1 key, k, with 2 children. Right? In other words, it's a regular binary search tree node, right? It's the usual binary search tree node. A 3 node is a node containing 2 keys. I'll call them K1 and K2, and 3 children. All right, such that if I've got 2 keys here and 3 children, then this child is going to be less than key K1. This child on the other end is going to be less or greater than K2, and this child is going to be between them. Right. So instead of me holding up fingers, let's go ahead and visualize that like generically. Right. So here's a 2 node. It has a single key, and it has at least 2 children, or an entire tree hanging off of it. And again, everything over here is less than K. Everything over here is greater than K. Right? That's the usual notion. This is a 2 node. What is a 3 node? It looks like this. K1, K2. It's got 2 keys in it. And the way that I like to visualize these is by drawing them as squares instead of circles. And then it has 3 children. Right? Everything over here is less than K1. Everything over here is greater than K2. Everything in here is going to be between K1 and K2, right? So X, right? It's going to lie between them. This is so that when you're doing searching, you come in and you say that I'm searching for this particular key. Let's make this a little bit more concrete here. 3 and 8. And then I'm searching for, say, 2. I come in here and I see, oh, well, 2 is less than the first key here, so I would go down that direction. Say that I'm searching for 7. 7, oh, that's greater than 3. Oh, but it's less than 8. I would go down in that direction, right? 7 would be down here somewhere. 2 would be down here somewhere. And if it's something greater than 8, then okay, I need to go that way. Say I was searching for 10 or something, right? And so this ordering allows you more children, more keys, and the other properties that we've just identified will ensure that everything is at the same depth, right? So it's a full binary tree, meaning that every node is there. It might be a 2 node, it might be a 3 node, but every single node is going to be there. And if you take a look at the review material, I didn't go over it yesterday, but if you've got a full binary tree where every node is there, then you are guaranteed that the depth is logarithmic with respect to the number of nodes in there, okay? Because it's full. It can't skew because every node is going to be there and every node is non-empty. So how do we actually work with this thing? How do we insert? Insertion. Insertion is always done in a leaf, right? If it is a 2 node, then you make it into a 3 node. If it is a 3 node, then you make it into a new, I don't want to say you make it into, there are some different situations here, but you promote the middle element up, potentially overflowing the parent, etc. Right? So I've got another visualization over here. Let me go ahead and find the same list that we did before. Let's see, where is it? Just because I don't like variety. Right? I'm fine with bland. I don't know about you. So here's 8. We insert that. That's just a regular old 2 node, right? We always insert into a leaf. That root right there is also the leaf. So let's go ahead and insert now 4. It becomes a 2 node now, or sorry, a 3 node. It has 2 keys, no children here, but that's okay because that's the one exception. When everything has to have at least 2 to 3 children, except possibly the root. Right? And we're just starting out here, so of course we have to have some configuration like this. Now, what if I go ahead and insert 7? So visually, what's that going to look like? Right? Let's go ahead and preview that over here, because I'm not sure what this will look like. The visualization, that is. So once I order them, 4, 7, and 8, that node is over full. Remember that we only have 2 nodes and 3 nodes. We have at most 2 keys here. All right, so what I'm going to do is I'm going to take the middle element and I'm going to overflow it or promote it upwards. And what's going to happen is once I promote it upwards, since it's empty, that's going to become a new node, and it's going to become a 2 node because there's only 1 key in it. That means that the children that were down here before, 4 and 8, can now be split apart. And so I will end up having a 7, a 4, and an 8. Okay? Let's see if what it looks like when we actually do this. There we go. And that's just a traditional, everything that is now a 2 node, and it's just a traditional binary search tree now. Let's continue. Let's go ahead and insert 3. 3 is less than 7, so it comes down here, and we always insert into a leaf. This 2 node then will become a 3 node. And that's perfectly fine because everything can be a 2 node, everything can be a 3 node. All of the properties are satisfied here. It had room to grow, so we were able to put both keys in there. Likewise, if we insert, if we insert 2 is next in my list. What's going to happen here is it's going to come down. It's less than 7, so it comes down in here. We always insert it in the leaf, so we're going to end up having 2, 3, and 4 here. Right? So 2, 3, and 4. And up here was 7, and down here is 8. There we go. This is over full because we can't hold 3 keys. We can hold at most 2 keys. So 3 gets promoted up here so that we have 2 and 4. 3 and 7, it'll look like this now. 3 and 7 will be up here, but that's now a 3 node, and it needs 3 children. Well, when we promoted this up, we made it so that there are 2 and 4 over here. 8 is still over here. Where could everything go? 2 is less than 3, so it has to hang off of here. But 4, since we promoted the middle element here, we know that 4 has to then swing over to become a child of this, because otherwise it can't be over here anymore because it's a greater than 3, the thing that we just promoted. So it swings over to become a new 2 node. There. We were able to accommodate that here because this node was a 2 node, and so we were able to make it into a 3 node. There was enough room. What happens when there's not enough room? We'll find out in a moment. There we go. Just as I said. What about 5? Where's 5 going to go? It's between 3 and 7, so it'll go down here, and there's perfectly happy making that 2 node into a 3 node, and now it has 2 keys. What happens when we insert 1? It'll come down here, it's less, and that'll become a 3 node. What happens when we insert 10? That'll make the remaining one over here a 3 node. At this point, we've got a full 2-3 tree. If we put anything else into this tree, then something is going to happen. What is that something going to be if it's 6? So 6 lies between 3 and 7, so it comes down here. And now we've got 4, 5, and 6. Okay? Let's look at it over here. 4, 5, and 6. And over here was 1 and 2. 8 and 10 over here. And up above, we had 3 and 7. Right? Yeah. So this is full. We kick it up to the parent to make, and we also, eventually we're going to end up separating these two into their own. 5 is now up here, right? But what does that look like? Well, now we've got 4 children. We can't have that. But up here we've got 3 keys. We can't have that either. So we continue the promotion. 5 gets promoted up, and it becomes the new root. It has now 2 children, 3 and 7. All right. Let me get another piece of paper. So 5 is now at the top. It has 2 children, 3 and 7. And the problem is we've got now 4 children down here. 1 and 2, 4, 6, and then 8 and 10. But guess what? we need 4 children here. 1 and 2, 4, 6, 8, and 10. So inserting into a full 2-3 tree could end up with a much a deeper tree that has now grown in depth by 1, but all the properties are still satisfied. Right? It's still full. It's still full with respect to the number of nodes. All the nodes are there. Therefore, it guarantees logarithmic depth. Let's go ahead and see it in action. Then a second promotion, and that's what we have there now. Okay. Cool. What about deletion? Well, searching, of course, we talked about that already. But deletion, deletion could you grab the min in the right tree, right tree, or the max in the lefter tree. And I say left or right because if you want to delete this node, then you have to replace it with something. And if it's or you want to delete a key, you need a key to replace it basically. And so you need to go down to the right subtree or left subtree. That's clear. But if you want to delete this key right here, and there's definitely going to be a left subtree and a right subtree, but you could also go into the middle subtree. So that's why I'm calling it lefter or righter tree. The choice is yours, right? So when you do that, you replace that key that you wanted to delete. It could leave a observation. First of all, an observation. Such an element is always in a leaf, right? Thus, we may need we may need to take care of that. The leaf could be under full now. We may need to exchange a key at the bottom. Right? And I hesitate to even get into this because there are just a lot of different cases. Instead, I would draw your attention to the notes, and there are not that one, but there are a whole bunch of just configurations here that you'll always end up deleting from a leaf node. And so if you've got a situation, here's the simplest situation where, okay, I'm empty now right here, but what I need is I need a key. So, hey, my sibling has a key that I can borrow. Promote B up, move C down, right? And now we're all 2 nodes and we're all happy again. What if you've got a situation like this where everything else here is a 2 node, or a 3 node? Basically, you're shifting a bunch of stuff over. So my sibling to the right can spare 1. B gets promoted up here. A gets promoted down, right? And if you look at this as a line, if you're going from here up to there, down to here, up, back up, and over, like if you just flatten that tree out, basically you're just shifting the keys over by 1, right? So there are various different situations here that you have to account for. Okay? But I do want to do the analysis because this is actually pretty easy, right? So analysis. Our claim is that a 2-3 tree has depth D being order log n. There we go. Okay. For that, let's get a little bit mathy. And I'll come over here. Blue seems to be working out today, so let's go ahead and just stick with it. All right, so let n be the number of nodes in a number of keys. Yeah, in a 2-3 tree. Right? What is the maximum value of n? Okay. With respect to the depth or the height or whichever one you want, and let d be the depth. Right? Remember that it's full. So the maximum number occurs when every node is a 3 node, right? That is, every node has 3 children and 2 keys. Right? It's full. And so how many keys total does it have, right? That's the thing that we want to get a hold on here, right? So again, take a look at a visualization here. We've got 2 keys in there, and this is of depth 0. It's full, so it has all 3 children, right? And there's the depth 0, meaning how many nodes do we have? We have 1 node here. What about the second level? Depth 1. Right? We have 3 nodes. And how many keys did we have up here? That's what I want to do. Number of keys, 2. And here we would have 1, 2, 3, 4, 5, 6. We have 3 nodes, 6 keys. Right? What about the next level? 1, 2, 3, 1, 2, 3, 1, 2, 3. So 9 nodes at level depth 2. And consequently, 2, 4, 6, 8, 10, 12, 14, 16, 18. Right? And you start to see a pattern emerge here. Well, it's pretty easy pattern because at depth D, right? How many nodes do I have? Well, this is following a geometric progression here. This is going to be 3 to the D, right? And how many keys? Well, just twice as many as in that. I'm only considering that level right there. Twice as many as there are nodes because everything has all their keys. Right? Everything is a 3 node. I'm trying to maximize the number of keys here. All right. Total up the number of nodes here, and that's going to be a geometric series, basically. But it's a finite series. It's a summation of I running from, or D, running from 0 up to whatever D we have. So maybe I will go I here. Going from 0 up to D of 3 to the I. And remember that this is the number of nodes, right? So if we take and multiply that by 2, then this is the number of keys, right? And this is the maximum number. So what I want to do is I'm saying that n is at most this thing. I want to solve for this in terms of D, okay? Hopefully you remember that in general, summation of a geometric series here up to n, let's say m of x to the I is going to be x to the m plus 1, and then down below we've got x, the base, minus 1, right? I believe. Let's go ahead and we'll ask Wolfram Alpha, right? Sum of, I don't know, x to the I of I running from 0 up to m. Yep, m plus 1. Oh, minus 1. I'm glad that I checked that out because I forgot the minus 1 over here. There we go. All right. So n is at most, now that I'm going to get a closed form solution of this, 2 times, x in my case here is 3. That's my base. 3 to the d minus 1 all over 3 minus 1 is just 2. Those 2's cancel out. And so n is less than or equal to 3 to the d. I'll take 1 onto the other side. Right? And now I take log base 3 of n plus 1 of, is less than or equal to d. Right? So I've got a lower bound on d here. I was getting an upper bound on n, which gives me a lower bound in terms of n on d. Right? Now we just do the same thing, but we assume the other direction, right? What is the minimum number of keys? Right? And that's when everything is a 2 node, meaning that you have 2 children, 1 key each. And this is the usual analysis of binary search trees. where n is at least, right? Here, summation of I equals 0 up to d of 2 to the I, and then 1 out front here, 1 key for each one of these nodes. So I'll omit that. And n, what did I write before? Yeah, n is at least this big. There, that's what I wanted to state. Because I'm getting a lower, I got an upper bound on n before. Now I'm going to get a lower bound on n. The upper bound on n gave me a lower bound on d. This will give me an upper bound on d. And we use the same one as before. Everything comes out to be 2 to the d plus 1 minus 1. In the denominator, it's 2 minus 1, so that becomes 1, and that disappears anyway. Same solution as before, n plus 1, 2 to the d plus 1. Oh, did I forget my plus or minus 1 over there? Oh, minus 1, no, plus 1. Should be a plus or minus 1 over here, but I think it's minus 1 over here, right? Oh, anyway, in any case, I don't know. I forgot. It's logarithmic is what we're going to come out to be. All right, I'm not being exact here, but anyway, take the log of both of these, and I'll get d plus 1 is less than or equal to log base 2 now of n plus 1. Just take negative 1 on the other side, and that gives you a lower, an upper bound on d. Down here we had a lower bound on d, and so we can say finally that d is less than or equal to log base 2 of n plus 1 minus 1, and it's sandwiched in here on the other end at log base 3 of n, whatever it was before, plus 1. Maybe there's a minus 1 over there, whatever. But by definition, this implies that d is going to be theta log n. And remember, that's why we don't write our bases when we write asymptotics. All logs are the same to within a constant. You can change, using the change of base formula, you can take a log base 2 and change it into log base 3, vice versa. Okay? All right. That's 2-3 trees. Again, there are dozens more of these things. You don't have to worry about them all, right? If you're really interested and you want to write an entire paper on all the balanced binary search trees throughout history, then great. We want to write a Wikipedia page on it or something like that. That's fine too. So let's see, what time is it? Okay. What order do I want to go in? All right, let's look at one application here, another application of trees, because you're going to be programming this. In this module, we're going to look at two more things. We're going to look at Huffman coding, which is an application of trees, and we're also going to look at hash tables. But since you have to program Huffman coding, I want to at least motivate the idea of Huffman coding before tomorrow. So this is where we'll end today. We won't get into the actual algorithm itself. I'm just going to set it up instead. All right. So coding theory. You need a little bit of background on coding theory. It involves two things. Either adding redundancy to ensure that information is not lost in a noisy channel, right? Or compressing information, lossy or non-lossy, to reduce its size. Right? So Huffman coding, obviously, we're going to be encoding things, so we're obviously going to focus on the second one. Just a note on the first one here. Coding theory, where you add redundancy, it's all over the place. It's in wireless networking. It's in networking, right? If you send a packet of information, a bunch of zeros and ones from location A to location B, there's a certain probability that some of those bits will be lost. A 0 might get flipped over to a 1, or a 1 might get flipped to a 0. And you want to be able to detect and maybe even correct those situations. Coding theory is used all over the place in order to add redundant information. You can always send it twice, send it 3 times. And now you are always you can arbitrarily decrease the probability that all of your information will get lost. But you don't want to do that, because now your 5G signal connection now becomes a 1G, if that's a thing, right? You want to add only a small amount of additional information. So here's the actual information that you want to send. You add maybe a logarithmic or a constant additional amount, and you can at least detect potential errors, or maybe even correct those errors. The simplest way of doing this is a checksum. Take a binary string, and how many ones are there? If there's an even number of ones, send an additional 0. If there's an odd number of ones, send an additional 1. Now what you can do is you can detect, you can't correct, but you can at least detect, did an even number of bits get flipped in that transmission? That's a checksum. Now you can go ahead and generalize that and send a checksum of like an MD5 hash or something like that for data integrity. Did something get lost in the transmission, right? That's one branch of coding theory. The other branch of coding theory is compressing information. And of course, everybody's familiar with this. Most people are familiar with the lossy compression, right? JPEGs or MPEGs, right? MP4s, right? MP3s, right? Even the signal, the live stream signal that I'm sending out, it's highly compressed because you can't take 30 frames per second. Every single bit shouldn't be transmitted, because as you can see above me, my background is not changing. So a smart compression algorithm can say that, well, that bit never gets changed, so we will just send a signal that entire section never got changed. And we only have to encode these pixels right here and send them once, and then some additional information that display those pixels for the next 3 seconds, right? And so there are ways of cutting stuff out. MP3s do this by cutting out high and low signals that supposedly the human ear can't hear. But you can but if there's too much compression, then you can kind of start noticing it. JPEG, for example, that has been encoded, highly compressed, has lost information. Some of the bits were thrown out, or some of the bits were approximation, or a collection of the bits were approximated in order to get rid of some of the information. And you see this all the time. That's why I say, I think it's an internet thing. I think it's a common slang, but it's potato quality, right? So if you've got low resolution stuff, highly compressed stuff, then you've got potato quality stuff. What we're going to be focusing on with Huffman coding is lossless coding, right? We want to, our goal will be to encode text so that common characters are encoded with shorter code words, right? That is byte strings, right? And longer or less common characters are encoded with longer code words, right? What this will mean is that we will not lose any information. No information will be lost, but potentially we will encode a text file, into a smaller file, right? And this makes sense because if you think about it, think about the ASCII text system. In the ASCII text system, every English language character, A, B, C through X, Y, Z, has 8 bits. Actually, real ASCII text is only 7. It's only 7 bits. But the extended ASCII text character system, nobody wants to deal with 7 bits. We all deal with byte addressing. So every ASCII text character has an 8-bit, 1 byte value assigned to it. Why? When you hardly ever use Z, right? T is the most common. Or if you watch Wheel of Fortune, RSTLE are the most common. And so why should we encode everything with the exact same number of bits when we can vary that, right? That some English characters are less common than others, right? So why encode them with the same amount of information? In fact, why encode them at all if they don't appear in the file that we're trying to send? If nobody ever used U with an umlaut, well, we can cut that out of our character system altogether because it's just English, right? Space is actually the most common character in actual English text files, as you'll find when you do your programming assignment. But ultimately what we're going to do starting tomorrow is we're going to build a code word tree, right? A tree that ensures that common characters have a shorter code word, right? That is, again, a bit string, and so I shouldn't say byte strings, I should say bit strings. Shorter code word, while less common characters have a longer code word, right? And the reason that we end up using a tree is because we want a tree ensures that we have a prefix-free encoding such that that no code word is the prefix of another code word. And it works out because it's a tree. We start at the root. One of the properties of a tree, a binary tree, is any tree, is that the number of paths from the root to any other node, and in this particular case, we're only going to be concerned with leaf nodes, is unique. If I go from this root down to this leaf and this root down to this leaf, at some point they might share an ascendance, an ancestry, but at some point they have to diverge. And if we base our code words on these paths through the trees, then we're assured that everything gets a unique code word and nothing is the prefix of another code word. I'll give you more details on that tomorrow.